So the last thing that I want to talk about is the temperature dependence of Planck's law. So if you take Planck's law for the blackbody radiation and we integrate it over all the frequency, we get the total radiation. And the total radiation, if you work this out, gives you something like this. So the temperature dependence is T to the power 4. Whereas this law, the temperature dependence of the total energy, is called Stefan's law. Now Stefan's law and sigma is called Stefan's constant, and Stefan's constant is given by 2 pi to the power 5 by 15 h cubed c squared kb to the power 4. Another thing that we can do is that we can ask what is the temperature dependence of the wavelength at which the blackbody radiation spectrum has its maximum. So remember that the blackbody radiation does something like this. So here we have the frequency, and here was the energy density. So this would be the maximum frequency, and this would give us the maximum wavelength. So if you go back to the expression that Planck derived, and you can derive from this an expression for the maximum lambda maximum wavelength, that is the wavelength at which the radiation reaches its maximum, and that times T will be given by a constant B, where the value of B, you can calculate it to be, B is given by HC divided by 4.965 kb. So why are we interested in this? So, by the way, this law is called Wien's law. So the reason why we're interested in Wien's law and Stefan's law is because we can you can do the experiments and measure these constants. You can measure sigma and you can measure B. And by measuring sigma and B, you can actually do an experimental measurement of the values of the fundamental constants Kb and H. H is called Planck's constant, and H has a value which in the CGS unit is given by 6.625 into 10 to the power minus 25 ergs second. Whereas in the MCAS unit, this is given by 6.625 into 10 to the power minus 34 meter squared kilogram per second.